Okay, so that's the last lecture. And because I've been talking to you about geomorphology in very general term, I was thinking that I could give you a last lecture on coastal geomorphology, focusing on one of my specialty. And also I will give you the point of view of the researcher. So not like a normal lecture, but just to show you so that you can see the kind of research that we do in geomorphology. So today it's about deciphering tsunami and palette or tsunami wave energy and orientation. And that will be actually the second part after a long introduction about the tsunami in Banda, Aceh. So what happened in Banda Aceh? Let me see if I can click. Yeah. So what happened in Banda Aceh, unfortunately, you can see you have the city right here, and you have Lucknow on the other side, and the wave went from two directions. The tsunami arrived in 2004, in December 2004 from that area, flooded Banda Aceh, and also the wave went around by Lucknow, so the wave was coming also in this way. So we have really two directions from the tsunami reaching land. And it resulted, of course, in a lot of impact. So on that map here, you can see the devastated urban areas in red, very strong here, and less and less. But you have actually a very big impact. A lot of people compare this tsunami to the Tohoku tsunami in Japan, but in Japan we had fewer population, so an estimated of 20,000 people died, but in Banda Aceh and Lucknow area alone, we are more around 200,000 people, so 10 times more. And not because we have better engineering or anything in Japan, but because we had a lot of people on the coast there. So as an introduction to that tsunami, that's a picture we took in 2005, just after the tsunami. And when you look at it, one of the first things you have to remember is when you do geomorphology, geomorphology is useful for the science itself. It's interesting, but you can use it in many different ways: for resource engineering, for hazards management, for planning. And this is an example also in hazard. So I'm not going to give you details about the hazard, it's just an introduction, but so that you can see how you can use afterwards your knowledge in geomorphology. So as I was telling you, one of the main problems is that we have the Banda Aceh plain area, which is right here. It's quite low, and it's filled with a lot of people. And because the area actually has a high density of population, a lot of young people, you can see them here sitting down, a lot of young people. So a large population, which has turned the hazard in an important disaster. And local people, if you look at some of the islands, let's say, if you look in those areas where you have Simelu Island and other islands, people know very well about the hazards, and we didn't have so many deaths there. But one of the problems we had in Banda Aceh was the war between the GAM and the National Army of Indonesia. So people, a lot of them ran away from the mountain to go and live by the sea. But those people didn't know so much about sea hazards. So when before the tsunami arrived, the sea retreated, and the people who ran away from the mountain didn't know anything about the sign of a tsunami. And that's why they didn't flee or run away from this. So that was another problem as well. Another issue was also the high density of population and then the deforestation. So all the natural barrier, like the mangrove that usually protects against tsunami, all of that was gone and was taken out by the local population. And when you look at it, that's how it resulted in. And one of the issues is that you can see that road here, because in Sumatra, if I have a map, yes, in Sumatra, you have the Barisan Mountain. There is only a small plain on the side. And because of that, we only have one road. And that one road was very important for relief and for help. But very often that one road was destroyed here, as you can see. So from this perspective, you can see that the hazards turned into a disaster for a lot of different reasons. But from a geomorphology perspective, knowing that building the road on the sand on the coastline was not safe in case of a tsunami, understanding the changes that we're going to have after the tsunami as well, and how it impacts the change in the landscape of a long period of time is very important. And that's what I'm going to talk to you about it from a geomorphology perspective today. I'm going to talk about the geomorphological consequences of the tsunami. So if you look at this aerial photograph that was taken from the UN helicopter just in 2004 by a friend of mine, you can see the river which was going out and straight. All of a sudden we have this band of sand which is right here, and then the river is forced to move the U around. So this has two consequences. First, the sand which is here has been remobilized by the tsunami. So the tsunami eroded a lot of sand and then redistributed the sand on the coastline. So we have a new coastline because of that. But at the same time, this river now has less possibility to bring the sediment and the water out. So it's going to flood some of the land which is around. And at the same time, what you can see here, this flooded area that you can see, it's the result of two things. It's the result of one, subsidence, so the whole land went down, and it's also the result of erosion. So the sediment, the soil were eroded by the tsunami. So when you think in terms of geomorphology, we have what we call a geomorphological crisis. It means that out of a long-term evolution, we have a peak of energy, and that peak of energy is actually creating a lot of changes very quickly, so that the environment has then to reorganize itself around it. And it affected the surface, but it also affected the ground, the subsurface and underground. And when you look at it here, you can see you have also the well pollution, or wells when you have several pollution. So the water was mixed. And one of the processes that occurred with the tsunami was when the tsunami, before the tsunami arrived, the water receded at sea. So it means that the pressure in the groundwater is going down. And with that pressure going down, the water level in the wells is going down as well. So you have already a first mixing of water, which is unusual in those wells. And then the tsunami rushed back. But when the tsunami rushes back, what you have to remember is that there is water underneath as well. So it's not only the wave, it's also the groundwater, which is pushed once again. So out of those wells, then sediment, water was pouring out due to the overpressure. So you have two impacts in terms of geomorphology. You have the modification of the ground surface, what you can see, and two, you have a modification of the underground. Things that you cannot see are being modified by the tsunami. And then if we go back to the surface, there are a lot of changes that are also unforeseen. So for those of you who have been to UGM University maybe before, you might recognize him when he was still a student. This is Dr. Angri from the Geomorphological Laboratory at UGM in geography. And you can see where he's standing. You can see the slab of a house. So we had the houses here, and we had the street, and people were living. He's on the side of it. And what you can see is the return of sand dune. So I was showing you in the first picture here, the sand is being transported by the sea and by the river in new locations. The wind is doing the same thing. It's creating new dune fields at new places. So you had dunes at one place, those have been eroded, dismantled, and then the new dune fields are being created somewhere else. So you see, you have this kind of snap evolution where things have been moving very, very, very fast. And then if you consider changes that take place over a longer term period, so this change here is very rapid, but it's also something which is going to build up over a short period. You have elements that have created change that will not be able to be restored or modified over a long-term period. So here we are in Lokna, and to situate it on the map, this is the area here. So that's the place you can see. And we have the village, which is right here, with the masjid, which is right here. And the masjid was not finished when the tsunami came, so the wall were not built. And you're going to see it's very important because it saved the masjid against the tsunami. When you look at the post-tsunami images, everything is destroyed except the masjid that stays. Aneh, right? So what happened there for the story is because there were no wall, but just the pillar, the column, the tsunami went through it and didn't destroy it at all. Unfortunately, the people who had come to the masjid to pray for God or Allah to save them, they were drawn in the masjid with the water. And to go back to my story here, what we can see is in the north of that area, this is the shoreline. And here you have some rock, which are cliffs that are on the side. And after the tsunami, you can see that the sand is gone, and the only thing that remains are the beach rock. So much harder. You can see some of them here as well. And you can see also the vegetation that has been eroded from the rock itself. So those kind of features here will take tens of thousand years, 100,000 years to come back if they do. And what you can see on the image here, if you go down in the field, that's how it looks like. So you have here the erosion due to the tsunami wave. And you have the erosion of the sand. You can see the roots here of the coconut tree, because the sand beach and the sand dune was much higher here. So that's another example. When you are here, you can see in Lampuk, still we have the masjid, which is still standing, which is amazing. And you have the beach rock, which is right there, the coast, which is right there. And you can see the beach rock, that line here of hard rock, which is popping up. All the rest has been eroded. And you can see you have some remaining of the coconut tree destroyed by the tsunami. And you can see the roots of that coconut tree here. On that photograph, you can also see those features here. You see that channel. You have another channel here and another channel here. Those channels were not there before the tsunami. If you want the proof, you can have a look at this. You can see there is no channel. And those channels have appeared because of the backwash. So the tsunami water comes in, it inundates all of that. So let me see if I can draw. I remember we can draw on PowerPoints. Yes. So the tsunami comes in. It's going to erode some of that material here, mix with sediment, houses, parts, and all the horrible things that the tsunami has destroyed. And then what he has to do is to come back. Okay, so that's called the run-up. Run-up, tsunami run-up, run-up. And when it comes back, so the water goes back to the sea, this is called the backwash. Back, CK, back, wash. And with the backwash, it's going to carry a lot of debris from the houses, a lot of bricks, a lot of wood debris. So it's going to erode again the coast, and it's going to create those features. So those are erosion features that you can see due to the backwash. Okay. So before I go further, I need to add one more word about run-up. So there is another definition of run-up. So the run-up I'm still not good with this. I don't know. So the run-up, there is another. Oh, yeah. Sorry. Yeah, when I click on it, you see, it's just not going. And I click left, I click right, nothing. All right. All right. So the run-up is another thing. The run-up can be also the measure of the wave height to the mean sea level. And it's not to be mixed with the wave height, which is the measure of the height of the wave compared to the ground underneath. To move that if I can. Okay. And put it in black maybe if I can as well. It doesn't work. Okay. So those are two different things. The measure of the wave height to the mean sea level, that's the run-up. Okay. So we take the measure here. Oh, it's draw, sorry. No wonder I couldn't do it. So we take the measure of the height here. So we have the sea level, which is going to be 0. And then we look at the wave coming up, up, and up. And the water reached, let's say, up to here. And we measure the altitude of this location. So we're going to have something like this, the altitude there. And that's 0, that's the mean sea level. And you see, that's here, the elevation, that's the run-up. If you want to measure the wave height or wave height, let's say if you're here, you're going to measure the topography at this location and the water height at this location. So you might have, let's say, 40 centimeters or 20, it was more like 20 meters at that time. And when you want to measure, let's say here, the maximum run-up, which may be, let's say, 35 meters. If you have a slope, if this is a slope, and the tsunami went, let's use some blue, and the tsunami went like this, what? The run-up in that case is going to be here, 35 meters. But the wave height is going to be 0 because this is the very end. So the water thickness above the ground is going to be very, very small. So the maximum run-up coincide with the wave height more or less equals 0 when you have no more wave height anymore. Okay, so just remember this because when I say run-up earlier, it was in a different sense. The run-up was the water coming in compared to the backwash, which was the water coming out. But there are other definitions. Okay, another impact which is changing soils and eventually how the geomorphology evolved is the presence of salt in the ground. So here you can see, I'm going to use that tool again now that I know how to use it. You can see the limit of the wave destructive power. So here we had a mixing, the wave flowing and jumping on the ground, destroying everything here. But the water afterwards, with less energy, went and continued here. So we have less energy because the trees are not dead or destroyed or uprooted. They are dead here because of the salt in the soil. And they don't like it when you have too much salt in the soil. So you can see that's another point I want to make about geomorphology and geomorphologist. So when you do geomorphology as a geomorphologist, you need to be able to also look at other elements to use them as clues. Here, as a geomorphologist, I'm interested in the wave movement and the wave energy. So this part, for instance. But from a ground perspective, you see, I cannot see much. There is very little evidence or anything. But the vegetation is a very good evidence of the processes that have occurred. And here you can see that power of eroding destructive power. And on the back here, you can see that, well, we have less of this. If I compare this to this area in that side, you can see the erosion of the tsunami in that location. And it's very important to understand how tsunami work. Tsunami, we always think about it as a wall of water coming our way. Well, it's not the case. It's more like tongues that go in one direction or another direction, following the topography on shore. And they are very seldom actually just a simple wall of water. In Lokna, we had up to the coast a wall of water. Then the wave broke, and then it changed direction and went in a lot of different directions. Oh, I haven't erased it. And as I was telling you in the introduction, and other geomorphologic effect of the tsunami has been the change in the estuaries and the change in the river mouth as well. So in that case here, the river mouth was also located just right here. You can see it through. So we had actually one channel here, and we had another channel in this location. And what is really interesting is that those channels, they are totally filled with sediments now. So we have the opposite problem. We have areas where the sediments are gone, but we are also sediments where they've been blocking now the waterways. And you can see from the evolution that you have a shoreline which is in creation here as well. So the water is coming out of the river, it's pushing through. But when you look at the fine sediments, you can see that you have this plume of fine sediments here. I'm going to. You have this plume here of fine sediment coming out, showing that you have stronger energy here. So the water flows through. You have another one here. But if you look in between, you will see that you also have those breakers here, break waves. That shows that it's not so deep here, and we have the construction here of this new shoreline. We might have other elements here and here. So when you look at those images, if you do geomorphology, one of the tools you might have to use are aerial photograph and their interpretation. And one of the things you can look at is, of course, the geomorphology, the shape of the landforms, but also the colors and tones as indication of the processes occurring in the area you're studying. And here very clearly, we can see actually the different location where the mouths of that river are located. So those are further destruction and the creation of the channels I was mentioning. And when we go down in the field, that's one of my French colleagues, you can see actually how it has been eroding through the soil and of the shorelines in this location. And this can be quite, the erosion actually has led to the destruction of the littoral vegetation, like it's the case here. I haven't erased everything, let me erase again, blah, 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 blah. And you can see again here all the tree roots in those locations. And other elements that we have seen are the coral reef blocks. So you see that block here that was taken from the bottom of the sea and brought up by the tsunami to the shoreline. The truth is that those coral blocks, they are not too heavy because they are made of coral and the density is quite low. But still, to carry such a raft of large material, you still need quite a lot of energy to do so. And when you zoom again on deposits, one of the things I can see are those different levels that have been deposited by the tsunami. And one thing that you have to remember is that if we have this idea that it was a big wave, what happened there was you had the wave coming in and then coming out and another one coming in and then another one coming out. And one of the research we did there and that you can do, and that's the next step, is to use the human elements that are present in those deposits to try to understand whether it's a wave that was coming in or coming out. In other words, when you have elements coming from the sea, like foraminifera, those small living organisms that are present, a lot of them are present, you can find them into the sediment, you have a good clue that it's coming from the sea. But when you have sediment which are mixed, let's say, with bottle or piece of destroyed walls, like it's the case here, so we have matched them, you have a piece of destroyed wall, you have broken glasses, you have a piece of a notebook here, little bottles that are preserved in the sediments. You know that to have those, you need the tsunami to have gone on land, gathered this material, and then come back. So one of my colleagues here is a specialist of anthropogenic sediment. So you look at very, very fine particles, especially pollution, to try to understand where the sediment have gone, how they have moved. So there is a lot of research on that to understand the geomorphology and the processes that create those landforms. And then to conclude on the erosion and deposition, this location here, this pond was there, but something is missing. And I'm going to draw it for you. What is missing here is Oh, sorry, draw, is this. So here we had a cliff wall, and all of that is just gone, destroyed by the tsunami. I have seen similar erosion pattern in the Tohoku earthquake, where walls that were not so big on the coastline, those cliffs have been destroyed by the tsunami. So you have those events that you don't see every day on the coast. So if I was to do a typical coastline or coastal geomorphology class, I will talk to you about the rip current. I will talk to you about the storms and the sand movement. But you also need to remember that those everyday life processes can be disturbed in a large and big way during one single event when you have a tsunami or when you have those high energy events. And understanding those and the relation with the geomorphology is very important, because then you can use those geomorphological hints. You can go in the field and look at the geomorphology to look at, oh, did we have a tsunami before here? How did that coast get destroyed? Or how did that cliff got to miss in this location? So those high energy events are very important to understand the evolution of the coastline. So to continue on that, I'm going to show you further examples that are out of research this time. And I'm trying to finish not too late, because at the end of the lecture, I would like to have Aditya also talking to you about one project that we have together, where we would like students from Indonesia to talk to students from Japan and exchange ideas around geomorphology and hazards and disaster risk, and how the two countries look at it. Okay, so I'm going to erase again, annotate, and erase. Okay. So the first thing is that a lot of the research which is being done is done in collaborative ways. And that's one of the reasons why I think it's nice for you to talk to the Japanese people. I like also talking to you or talking with you. I hope it could be more of an exchange and I could hear more of your voice. But most of scientific research is done through large teams and through with different groups, like what we are doing here. And very often we cross data from different countries to try to understand the processes that we see, like the coastal processes. And one of the way we do that to try to understand the previous work or the previous processes from the deposit is to look at the sediment and the sediment structures as an extra element. So what we have done, for instance, in this example, is to go with what we call a geoslicer. So it's a small core, but it's square and thin, where we take a slice of sediment and take that slice of sediment out. And here we are in the Tohoku area. And what we have done is to use a machine, which is the Kappa bridge, to measure the orientation of the sediment. So basically, if the sediment are oriented in one direction or another direction, then we know that they have been pushed by a wave going this way or a wave going this way. So using those, we can reconstruct the surface processes. It can be used for tsunami, but it can be used for tsunami, but it also can be used for river floods or any other event you are interested in. In New Zealand, we use the same method also here in Hawke's Bay. So we were with Dr. Aditya Saputra in Christchurch together when he was younger and I was also younger. And one of the research we did with a colleague of mine and some students who were driving the research was to look in this location in Hawke's Bay, take series of calls and data from outcrop like this ones here. And from that, we did the same measurement on the sediment to try to understand how the wave and the tsunami and the water went up that small bay. So we have the small bay here, and we have this area that we know has been inundated by a tsunami in the 1960s. So what we did is to go and take sediments, and from those direction, then we could reconstruct the direction of the tsunami waves for an event that we didn't see. So for Indonesia, for instance, you have a lot of tsunami and tsunami deposits that are located in many different places. And one way of looking at your tsunami deposit to understand what was the process at play is to go back, take core, and look at the orientation and the tilting of your tsunami deposit. So if I go back to Banda Aceh, for instance, so that's the location where I show you the area and the destruction before. What we did is the very same kind of work, and using those information on the direction of the waves. So you see, we could reconstruct all of those directions. The color of the arrows depends on the type of evidence that we have used, but it's another problem here. But let's say that we can construct arrows and have an idea of like what was the main direction of the tsunami. And from that here, you can see very clearly that the tsunami went around that location. It went here, then you have something which is a bit higher. You have hills here. So the tsunami went around the hill and down in that location. So you can really follow the pathway of the tsunami. And another location where we did something similar with some of my colleagues and also with students from Indonesia as well who were in France. So I did some simulation of the Krakatoa eruption and tsunami wave going around the isthmus. And here we have the Laban Isthmus. And at the Laban Isthmus, we have tsunami deposits that have been created by the 1883 Krakatoa eruption. So what we did for that is to take sets of sediments, one on top of another, and to look at the orientation of the tsunami. And for that, we use the AMS methods here. And from that AMS method, we could see that the tsunami had gone straight from the volcano towards, no, it's not this. Straight from the volcano into the Laban Isthmus. But we also had waves that had gone all around and attacked from that side. And what you can see here, so here you have the Krakatoa, and on this side you have the Indian Ocean. We have tsunami deposit like this one, the green one, that went from that direction. Actually, I think it's the opposite, sorry. I'm saying something wrong. The Krakatoa is on the other side. So that's the Krakatoa side, yeah. And that's the ocean side. And you have the first wave that comes in and deposits this one. So that's the first wave here. And then we have a second wave that comes in and deposits this one. And we think that the tsunami deposit was actually over as well, because we can find some of it here and some of it here. So we have erosion in between. And then when we look at this one here, we know that it has come from the other side. So we have Krakatoa side, and then it went around the isthmus from the ocean and deposit sediment, and back and forth and back and forth. If you were to look at those sediments only, you cannot say whether it's coming from one direction or another. But when you use this AMS method, this tool here, then you can define with precision where the material comes from. Okay? So that's another tool for you as a geomorphologist, is to be able to use the sediment. So I was telling you, see, you use the landform, but you use also the vegetation, and you also use the subsurface and the subsurface structure. So those are the details of some other results. Let me not go into that. we have the same kind of things where we look at different tsunami. And for that last one, what is really interesting is that in the location in Japan where we caught, what we can see is the 800 years ago Jogan tsunami. So we had a big tsunami before, and we could sample it the same way. Okay, so it's going to be all for me for this set of class in geomorphology. I hope you enjoyed it. I hope you're going to have a new vocation to become geomorphologist. I think geomorphology is very important. You can find it maybe, oh, it's boring, not so interesting. The things like, that's why I did this last lecture. Geomorphology is at the heart of a lot of other sciences, like natural hazards, I was telling you, like environmental science, or also resource management, and understanding geomorphology for that is very important. The other thing is that Indonesia has now a lot of geoscientists as well, but you also have a lot of foreigners coming in, and it's important to have local specialists who can work and collaborate with the foreign researchers. It makes the science much better, much more interesting for everyone else. So now it's 11:45 on my side, so it's 9:45 on your side. So we have 15 more minutes, and I'm going to ask Aditya if he's around, if he can say a few words about our program and our idea to get actually different groups together to discuss different topics on hazards and disaster risk between Japanese and Indonesian. So in Japan, I have 6 teams that will participate in this. And what I will do is to record the meeting that each team will have, because it will be part of the grade my students will get at the end. Thank you.
Thank you, Professor Gomez, for your lecture. Teman-teman semua, jadi di hari Senin nanti, di hari Senin, is it Monday, yes, Chris? Is it Monday morning, 7:30, 7:30, kita akan mengadakan student international meeting on disaster. Jadi nanti ada 30 peserta, itu yang akan saya buka pendaftarannya setelah kuliah ini. Kita batasi 30 peserta karena memang akan dibagi dalam bentuk 6 tim. Setiap timnya nanti ada sekitar 5 atau 6 orang dari Indonesia dan juga dari student dari Jepang, dari Kobe University. Nah, nanti kita diskusi terkait tentang disaster, ada gempa bumi, ada tsunami, ada longsor, ada banjir, dan ada multi hazard. Tentu saja di Indonesia dan di Jepang. Nah, nanti akan ada pertukaran informasi terkait bagaimana disaster tersebut terjadi di Indonesia dan juga di Jepang. Bagi yang mereka ikut 30 peserta tadi, kita sudah sepakat dengan Profesor Gomez akan kita beri nilai tambah, nilai lebih, nilai additional mark pada mata kuliah geomorfologi dasar ini di nilai akhirnya nanti. Jadi jangan sia-siakan kesempatan ini. Setelah kuliah ini selesai akan saya share ke kalian, ke ketua kelas masing-masing, pendaftarannya, dan kemudian kita berkoordinasi melalui WhatsApp group. So, and then in Monday, Chris,
I was thinking maybe not next Monday, but Monday in a week, in 9 days' time, so that students have time to get ready. Otherwise, it's a very short. What do you think?
That's good. Or maybe we can in the next week, Thursday.
Yeah.
So we can do it whether on 19 July, or in Tuesday of 16 July. Which one is suitable for your student and you?
I think that Monday is better for the students.
Monday 19.
Yeah, because they have other classes. If it's too far away, we can. I can always arrange over the weekend. That's not a problem. I was thinking about the logistics side.
Let's set on Monday 19. Is okay for you?
Yeah, Monday 19 is very good.
Oke, Monday 19 Juli. Oke. Jadi ternyata 2 minggu lagi. Jadi kita ada persiapan. Nanti setiap student bisa mempersiapkan